Okay, let's see one more example. You are being given the inner product of AB to be 1 by 2 and CD to be 3 by 4. But asked to evaluate the inner product of ket xi and phi, where ket xi is defined as a tensor product between ket A and ket C. Ket phi is defined as tensor product between ket B and ket D. Let's see how to do it. Uh, Tensor product of ket xi and ket phi is something like, just see, I can separate it, guys. A tensor product is just the multiplication. Okay. So it is something like this. Ket phi is as it is, guys. But for ket xi, I'll be needing its dual. Okay. So the dual of ket phi, that is bra xi, would be, see how will it be? Uh, dual of dual of ket A, dual of ket A, tensor product, dual of ket C. Okay. So the same thing I will write in this. So what I'll have, dual of ket A, okay, tensor product, dual of ket C, okay. Now this is the value of ket xi, guys. Okay. This is one half. The other half is ket B, tensor product of ket D, guys. Okay. Yeah. Now you know how tensor product operates upon. Okay. Yeah. So what happens would be first one for the first one, second one for the second one. So it is ket A, bra A, ket B. Okay. Bra A, ket B and bra C, ket D. Okay. Or I need not write two lines. It is just a inner product of AB and inner product of CD, guys. So it's nothing but 1 by 2 into 3 by 4, which gives me 3 by 8. Okay? Yeah. Now, in this very same question, if you are being asked whether you can find the outer product. I leave it for you to check whether you can find the outer product of it. Okay? How do I write outer product? This is how I will write outer product. Can you find outer product is the question. Okay. For outer product, just see here, I'll be needing ket xi as it is, guys. Dual of ket phi is what I'll be needing. Okay. So what would be dual of ket phi? Dual of ket phi would be something like dual of ket B, tensor product, dual of ket D. Okay, yeah, insert the same. What I will be getting would be ket A, tensor product of ket C into dual of ket phi. Okay, dual of ket B, tensor product, dual of ket D. See what happens, guys? Yeah. This one to this and this one to this. So what I'll be getting is in an outer product of this into outer product of C and D. Okay. If you have the values for it, you will substitute. If you can get the values for it, you will substitute. Otherwise, you can. Okay. There's one more interesting question that I have done, guys. That I'll be doing now. I've written some basic things about it so that I can speed up the video. What that is using the Bloch-Spear definition, you write the same, superposition state in terms of cos theta and sin theta, or derive the Bloch-Spear representation for a superposition state. If you are being asked, how do I start with is what I'm trying to look into. Now, usually, guys, we have for a sphere, if I'm talking about a sphere, usually, if I'm talking about a sphere, okay, there are this three dimensions x, y, and z. Okay. Of course, spherical coordinates also comes into when spherical coordinates come into picture, guys. You rewrite for x, y, and z. The spherical coordinate system for x, y, and z, as you will be aware, would be sine theta cos phi, sine theta sin phi, and cos theta. This is my x, this is my y, and this is my z. Okay. Now, I'll be considering sigma. What exactly is sigma is, another version of writing this Pauli gates are also called Pauli operators, guys. Okay, another version of writing them is using, there is this version of capital X, capital Y, and capital Z. Along with that, sigma X, sigma Y, sigma Z is also being used when you talk about them as operators, guys. Sigma X is Pauli X operator, sigma Y is Pauli Y, sigma Z is Pauli Z. Now, in terms of these operators, sigma along the three directions, if you are asked to define, I mean in terms of vectors or in terms of the spherical notation, sigma bar is nothing but sigma x I cap, sigma y j cap plus sigma z k cap. Now, if you are asked to find how sigma n looks like. Sigma n is nothing but the sigma bar into the unit outward normal that emerges out of the sphere. Okay. Now unit outward normal have x, y, z directions, right? X, y and z are in terms of spherical coordinates. So sigma bar would be sigma xi cap, sigma yj cap, and sigma zk cap, and then n cap would be sine theta cos phi, sine theta sin phi, and cos theta k cap. Okay. Now if I take the dot product between these two vectors, I'll get something like this. Now sigma x is Pauli x gate. The not gate, it flips 0 to 1 and 1 to 0. Get 0 to 1 and get 1 to 0. Coming to Poly Y gate, it flips. There is a phase flip along with the state flip. Here the state ket 0 is flipped to ket 1, guys. Ket 1 is flipped to ket 0 in X gate. Okay. Here see, if I take out I common, 0 1 minus 1 0 is what I'll get. It has become minus also, na? So there is a state flip, state from ket 0 to ket 1. There is a flip also, there is a phase flip. Okay. That's what is Y gate. Now coming to Z gate, there is no state flip, guys. There is only phase flip because there is a change in the sign. Okay. Second matrix is my Y, Pauli Y. Third matrix is my Pauli Z. All these operators are Hermitian, guys. The operators that we define in quantum are all Hermitian. You can check, of course. I've done a video on what is Hermitian matrix. How do you check for? Yeah. Now my focus is on how do I get that cos theta, sin theta kind of notation, or that what is the Bloch-Spear notation for which I am doing this. Now multiply sin theta cos phi to the matrix. So I'll be getting 0 sin theta cos phi, sin theta cos phi. Okay, 0. This is my first matrix, guys. Second matrix would be 0 minus I sin theta sin phi. Okay, yeah, I sin theta sin phi and 0 plus cos theta 0 0 minus cos theta. That would be my third matrix. Add all the three respective elements you will be adding. So first element would have 0 0 and cos theta. Second element would have sin theta cos phi minus I sin theta sin phi. Of course, third one is 0. Okay. For the second row, first element, sin theta cos phi minus, no, plus I sin theta sin phi. Okay. Third element is 0, 0 and minus cos theta. Minus cos theta. What is this? This is my sigma n, guys. Now if I start finding the eigenvalues for it, how do I start? Characteristic equation. Characteristic equation is nothing but det sigma n minus lambda I is equal to 0. what that would be is cos theta minus lambda. Of course, this can be, sin theta can be taken common and written as e power minus I phi, guys, using De Moivre theorem or cis. Okay, here I can take out uh, cos phi and sin phi, guys. This is phi. Okay, again I can take out sin theta and write it as e power I phi. De Moivre theorem again, right? Yeah. Minus cos theta minus lambda. This is the determinant that I need to evaluate. Okay. I know when I have A, B, C, D, AD minus BC is my determinant. So what happens here, guys? AD would be what? Cos theta minus lambda into, there's a minus sign common, cos theta plus lambda. Okay. Minus, see this term? Sin theta into sin theta is sin squared, guys. Sin squared theta. E power minus I phi, e power minus I phi into e power I phi. This becomes e power 0, which is 1. This is equal to 0. Okay, let's see what happens. Okay, yeah. There's a minus sign common for both. I can remove. Now, this is something like a minus b into a plus b. So, a squared minus b squared cos squared theta minus lambda squared plus sine squared theta. Now, what happens to cos squared theta plus sine squared theta, guys? Its value is 1. So, 1 minus lambda squared is equal to 0 implies lambda is equal to plus or minus 1. These are the eigenvalues for the Bloch sphere representation, or these are the eigenvalues for sigma. Okay, yeah. Let's find out the eigenvectors as well. For lambda is equal to 1, let ket xi be the eigenvector. Okay, I already shown in the previous video how to find eigenvectors, right? So, sigma n ket xi, this is equal to 1 into ket xi, guys. Xi1 also I can call, fine, okay. What's the Xi1 I can define? Alpha 1, alpha 2, anything you can define, yes, beta 1, beta 2, for ket Xi2 also you can define. Just to make things uniform, I'm using, of course I can use, guys, here alpha and beta also I can use, guys, okay. So what happens, what's my matrix is cos theta minus 1. Okay, sine theta e power minus I phi, sine theta e power I phi minus cos theta plus 1, of course common I have taken, into, what's this, alpha beta, this is equal to alpha beta. Write it down in terms of equations, guys. Let's see what happens, okay. Alpha cos theta minus alpha plus beta sine theta e power minus I phi. This is equal to alpha. Okay, yes, this is what I will get. I can rewrite all alphas at one place. Okay, of course, just a second. If I put a minus 1 here, there'll be 0 here, guys. I'm sorry. Just see here. If I directly substitute, I'll write, wait. Okay. This is 0 and this is 0. If I directly substitute, just see here, guys. Sigma n minus lambda I into ket xi 1. This would be 0. This is the version that I have written. Okay, so that's why right side should be 0. Now, again, there is no alpha here. That's the reason here I'll be getting it to be, this to be 0. Now you see beta sine theta e power minus I phi. This is equal to alpha into cos theta, alpha into 1 minus cos theta. Okay. Minus alpha into cos theta minus 1. I can write like this. Now you see, guys, here I can write like this. Just see, beta sine theta can be written as 2 sine theta by 2 cos theta by 2. Yes or no? E power minus I phi, this is equal to, of course, I'll take out this 1 minus cos theta can be written as, 1 minus cos theta can be written as 2 sine theta by 2. 2 sine theta by 2. Time. These things go off. Beta cos theta by 2 e power minus I phi. This is equal to alpha is there for me. Okay. 2 sine square theta by 2. I'm sorry. Sine square theta by 2. So alpha sine theta by 2 will be remaining. Now you see the above equality. See, I'm saying LHS is equal to RHS. When can this be possible? If you try to correlate, if alpha value is equal to this and beta value is equal to this, then both can be equal. Okay. So let alpha is equal to 1 second. I will rewrite in a little better way. That is e power minus I phi is there na. I can take it towards the right. That's what. Okay. Beta cos theta by 2. Okay. Yeah. This is equal to alpha e power I phi sine theta by 2. I can write like this now. This one I have taken towards the right. Now you see alpha should be this, beta should be this. For the inequality to exist. Otherwise, everything is 0. This is possible only for alpha is equal to 0 and beta is equal to 0. And then getting a trivial value, I need not do so much of hard work. Alpha is equal to cos theta by 2. Beta is equal to e power I phi sine theta by 2. What I will write here, see, the above equality is possible only for alpha is equal to cos theta by 2, beta is equal to e power I phi sine theta by 2. Okay. This is how we will be proving it. Now, just see here, guys. Actually, I started with ket xi being equal to alpha ket 0 plus beta ket 1, the superposition state. Okay. Now, alpha I have got it to be theta by 2 into ket 0 plus beta I got it to be e power I phi sine theta by 2 ket 1. Okay, this is one version. I mean, for lambda is equal to 1, I get this. Now, for lambda is equal to minus 1, just see here. What's that? Sigma n ket xi 2, this is equal to lambda 2 ket xi 2. Okay, I will say lambda 2. Right. Now, what I will get would be cos, instead of minus 1, I'll be getting cos theta plus 1. Sin theta and e power minus I phi doesn't change. Okay. Sin theta and e power I phi also doesn't change. Yeah. Here cos theta minus cos theta plus 1 is what I will get. This is into alpha beta is equal to 0, 0. Okay. Yeah. Ket xi is all about alpha and beta only, right? Yeah. Of course, I can call them to be right. Now, alpha cos theta plus alpha plus beta sin theta e power minus I phi. This is equal to 0 is one version. Another version is alpha sin theta e power I phi minus beta cos theta plus beta is equal to 0. This is another version. Now again the same thing, guys. I write all alphas to one side, I write all betas to the other side. Just check what happens. Okay. Now what happens is, same thing, beta sine theta e power minus I phi. This is equal to minus alpha cos theta plus 1. Okay. Yeah. So again, for this inequality to be equal, I equate. What that is beta should be equal to cos theta kind. Okay, look at the second one. I think second one looks a bit better. Alpha sine theta e power I phi. This is equal to beta into cos theta plus 1. Okay. Yeah, of course, again, I can write that expansion, guys. What that is alpha sine theta can be written as 2 sine theta by 2 cos theta by 2 e power I phi this is equal to beta 2 cos squared theta by 2. So cos squared goes off, 2 also goes off. What I'll be left with is 2 sine theta by 2 e power I phi is equal to beta cos theta by 2. Now simple, again for the equality to exist. Yeah, I can take e power I phi this side or leave it like that. Now what I'll be getting is beta should be equal to sine theta by 2 e power I phi. Alpha should be equal to cos theta by 2. Yeah, have I got the same thing like before? Yeah, guys, just see here. Alpha is equal to cos theta by 2, beta is equal to e power I phi sine theta by 2. You can check the same thing here as well. Please see here. Yeah. Okay, this is how I will get that version of the Bloch sphere version. What that is cos theta by 2 get 0 plus sine theta by 2. Of course, e power I phi is there, get 1. This is the Bloch sphere version of writing a superposition state. Okay. Yeah. We'll look at another problem, guys. We'll look at another problem. What that is quantum entanglement. How, when do I talk about quantum entanglement? Also, the Bell states, EPR states or Bell states show the property of quantum entanglement. Guys, that we will talk quantum entanglement. Okay, quantum entanglement. What's the definition for quantum entanglement is? Suppose if I have a superposition state, superposition, the tensor product state we have, once I find the tensor product, what happens is one state gets entangled with the other. Okay. What exactly is quantum entanglement? Once if I tell and then proceed, it will be good. What is quantum entanglement? Suppose we have the tensor product of two states ket phi 1 and ket phi 2. Okay. Now I'll denote that by ket xi, guys. Ket xi is equal to ket phi 1 tensor product ket phi 2. Okay. Now, the resultant space, this suppose if I get something like ket xi, if I get something like A, B, C, D, okay. If I get something like this, then what I will say is, how I will check for entanglement or not is, there's a condition. The state is entangled. Listen properly. Entangled only if AD not equal to BC. Okay. If AD is equal to BC, what will you say if you ask me? If AD is equal to BC, then the resultant state is said to be separable. Okay. Or it is also called product space, guys. Product space. By the way, here let me put just one sentence, that is, quantum mechanics is all about atoms, electrons, kind of things. Or in other words, quantum mechanics talks about energy being propagated in terms of waves or atoms or electrons, kind of things. Now, once I say that two states are entangled, that means what? Looking at one, I can predict some properties about the other. Okay. Some states, if they are, if two states are entangled, looking at one, I can predict about the other. If they are not entangled, then after certain time they can be separable. They get separated. Like the people who have the same frequency kind of mindset. Okay. Yeah, let me not talk about more about this. Let me stick on to the problems that can be expected on this. There are this EPR states, guys. EPR states or the Bell states. What are those Bell states? You look here. Denoted by beta 0, 0, beta 0, 1, beta 1, 0, beta 1, 1. Okay, how they are defined, you ought to remember, guys. Okay, this is one. Yeah, of course, you can just predict, I think, looking at it. 0, 1, 1, 0, guys. And here it is 0, 0, 1, 1. And here it is 0, 1 minus 1, 0. Okay, of course, there is a by root 2 for all the terms. By root. Also for your Hadamard gate, there is a by root 2, guys. Okay. Now you ought to check whether the states are entangled or not, guys. How do you check? Using the condition, I'll be checking. Okay. Yeah. I'll write the matrix version. Just see here, guys. Of course, this is a tensor product, this is a tensor product. Okay, you should be able to guess. In case you have a doubt, I will write here. Just see ket 0, ket 0. Again, this is a tensor product shortcut, guys. Shorthand notation. Okay. So, what I will be getting is, it is something like 1, 0, 1, 0, 1, 0 tensor product. How will it be? Just see. 1, 0, 0, 0 it will be for the first one. For the second one, it is what? 0, 1, 0, 1. Okay, yeah. So what happens is it is 0, 0 and 0, 1. So if I add both of them, what I'll be getting would be, I'll write the resultant, just see here, 1, 0, 0, 1. Okay, of course, 1 by root 2 is there. For this one, the value is for 0, 1. The value is 1 by root 2. This is also 1 by root 2 only. 0, 1, 1, 0, guys. 1 by root 2, this is 1, 0, 0 minus 1. Okay, and this is 1 by root 2, 0, 1 minus 1, 0. Okay, now how do I check whether this Bell states are entangled or not? This is of the form ABCD. So I check for AD minus BC. Beta 0, 0. If I check for AD minus BC term, what happens? What's AD minus BC? 1 AD, I'm sorry, AD not equal to BC, guys. Okay. So 1 not equal to 0. Perfect. Not entangled. Separable. No, just a second. What I've got is correct only. AD minus AD and BC. Yeah. AD not equal to BC, entangled. Okay. Yeah. For beta 0, 1, you can see the definition again. For beta 0, 1, again, what's it? 0 is equal to 1, not equal to. So entangled. Beta 1, 0. Just see what happened. Minus 1, not equal to 0. So not entangled. Entangled, I'm sorry, not separable. Beta 1, 1. This is equal to what? 0, not equal to minus 1. Hence, all the four EPR states are entangled. By the way, to answer such kind of questions, you need to remember first of all the EPR states, guys. Okay, so do check them. Put a shortcut how to remember those EPR states, and then accordingly you can conclude saying the EPR states are all entangled. Okay, they are not separable, they are all entangled. Okay. I've done 3 questions. I think one more also I will do. The postulates of quantum mechanics. postulates of quantum mechanics. In a broader sense, there are four postulates, guys. What exactly those postulates are, you know, by the way. Okay, just let me tell you so that you remember. The first postulate is nothing but what it says is usually in a quantum system, no, usually the state of a quantum system, usually state of a quantum system is a vector, of course, is a vector. Ket xi, of course, t why I am writing, it can vary as well. It need not be a constant always. In a Hilbert space, in a Hilbert space, okay, what is this? This ket xi of t has all the information, has all information about the info, about the system, about the system at any time t. Okay. Also, the best part I have discussed, but then again, also, ket xi inner product will always be 1. That means what? Ket xi is always orthonormal. Okay. In such a case, we call ket xi such vectors to be state vectors, guys. State vectors. Okay. Also, I have written in the Bloch-Spear representation in qubit. Qubit in two-dimensional complex. Why complex? E power I phi. E power I phi is cos phi plus I sin phi. In two-dimensional complex space, if I have to write a qubit, of course, I shall write it as, of course, it's in complex because it's in Hilbert space, guys. Hilbert space. Okay, it's ket 0 plus beta ket 1. Of course, this condition is satisfied. Mod alpha square plus mod beta squared is equal to 1. Okay, normalize. It's a normalized vector such that mod alpha square plus mod beta squared is equal to 1. First postulate is all about the description of the state of a state in quantum mechanics, guys. Of a state. How does a state look like? What exactly are the properties? Next, the thing is about operators, guys. Operators. The second postulate is all about operators. What's it? For any dynamic variable. Dynamic means the thing that keeps changing. Okay. To every dynamic variable, A, okay, A is usually called a physically measurable quantity. Okay, physically measurable. For a dynamic variable, there corresponds an operator. For every dynamic variable A, there corresponds an operator. Operator A. The beauty of it is A is always Hermitian. A, which is Hermitian, guys, which is Hermitian. Okay. And the thing is, once it is Hermitian, I can go for its spectral decomposition. What is spectral decomposition? Finding the eigenvalues, splitting A into its, splitting or rewriting in its eigenvectors. Okay, hence, also how these eigenvectors are, that description is also given here. And its eigenvectors form a complete orthonormal basis. Complete orthonormal basis of the vector space. Okay? Yeah. This is all about the operators in the second postulate of quantum mechanics. Now coming to the third postulate, guys. What is third postulate? It talks about the measurements. about all the measurements. Anyways, we didn't have only specific things we'll talk about. Okay. Uh, the possible results of a measurement of a dynamic variable are the eigenvalues only. That's how I am talking about spectral decomposition and all. Okay. The possible results of measurement of a dynamic variable A are the eigenvalues an of the operator A. Whatever operator or matrix that I am considering, its eigenvalues I'll take. Okay. Now, the possible results of the measurement of a dynamic variable A are the eigenvalues an of the operator A corresponding to that variable. This operator is nothing but it corresponds to the variable A. Corresponding to the variable. Okay, of course, that's obvious. Anyways, now, if there are this eigenvalues, what will I do is, by spectral decomposition, we can rewrite operator A as A in terms of its eigenvalues, and of course, once I say eigenvalues, projection operators also come into picture, and corresponding projection operators. Corresponding projection operator, see here, Pn is given by outer product of Un. Okay, and A, how do I write? Just see here, summation n An Pn. An is nothing but my eigenvalues. Pn is nothing but the outer product of the eigenvectors, guys. Okay. Ket Un corresponds to the eigenvectors. Now, once I have done this, the probability also I can calculate. The probability of obtaining measurement of An is probability of An. How do I write it? Just see here, guys. Pn. This I will write. Okay. The spectral decomposition kind. Of course, the projection way of writing. Tr. Expectation also I can say this one. Okay. The outer product of Ketzai. Okay, yes. Trace of Pn into outer product of Ketzai. Okay. Yeah. Once I have obtained the measurement. Okay. Next thing is, after measurement, how things will look like, I should predict, na? The amplitude, the probability amplitude, if you ask me to amplitude, Cn is given by Un, inner product of Un and Ketzai. Okay. Now, this gives us the probability of obtaining measurement An. Probability of getting measurement An, just see here, how do I find it as inner product of this by the inner product of Ketzai. This is nothing but Cn squared by inner product of Ketzai. Okay. So Ketzai after measurement, how does it look like if you ask me? Of course, Ketzai is anyways, this one is 1, guys, always. Okay. Yeah. So it just, Cn is nothing but this wave function, guys. So finally the probability collapses to, once Ketzai is orthonormal, once Ketzai is equal to 1, the measurement result collapses to just wave function, collapses to the wave function. Okay. Yeah. Now you see Pn, this projection operator you can see. Projection operator you can see the outer product of Un. Okay. Now after measurement, how Ketzai looks like? After measurement, how Ketzai look like is Pn Ketzai by under root of expectation. Okay. This is how it looks like. Okay. Yeah. Once this is done, third postulate talks about measurements only, guys, in different versions. Once in terms of eigenvalues, then in terms of eigenvectors, then in terms of projections, then in terms of probabilities. Okay. Of course, finally, once the given state is normalized or orthonormal, the measurement just reduces to the wave function. Okay. Yeah. Now there's this final postulate, fourth postulate. It depends on the Schrodinger equation. All of us know if I say Schrodinger, it's all about the wave. And then once I talk about quantum mechanics, we talk about waves only. Quantum mechanics in a way is about study of waves only. Okay. So now you see the fourth postulate is time evolution of system. Time evolution. The best part of a quantum system is evaluating at any time the value. Okay. Not just after the coin landed or something like that. Okay. Yeah. The time evolution of a closed, the time evolution of a closed quantum system is governed by Schrodinger wave equation. Is governed by Schrodinger wave equation. Okay. Yeah. How does this equation look like? IH dou by dou t Ketzai. This is equal to H Ketzai. Okay, rate of change with time. Rate of change of Ketzai with time. I can clearly see, right? What is H? If you ask me, it's Hamiltonian, guys. What is Hamiltonian? Simple. In a layman language, if I have to say, see, if your given matrix is Hermitian, it is fine. Otherwise, I'll transform it to a Hamiltonian matrix, where always a Hamiltonian matrix is a Hermitian matrix. How do I transform it? There are things, of course. Okay, the operator corresponds to the total energy of the system. Okay, H corresponds to the total energy. Total energy. Okay, yeah. Now, the state of the system at a later time. At a later time, the state of the system is given by ket xi of t. This is equal to e power minus I h t by h ket xi 0. Okay. Later time, it is governed by the previous time. Or in other words, I can write in terms of unitary operator as unitary operator. In terms of unitary operator, I can write it as u is equal to e power minus I h t by small h. Okay. Again, the capital H is the Hamiltonian. Hamiltonian is the total. I mean, it describes the total energy of the system. Okay. Yeah. These are the postulates of quantum mechanics, guys. Yeah. With this, I'll end this video. I'll do some more numerical examples in the next video. Thank you.